Welcome back everyone. In this lecture I will construct the regular representation of G, and then using the regular representation, so we actually prove that the irreducible characters, they form a basis for this space of class functions. So let us begin. So I already told you like what is the regular representation. So let me actually quickly recall what it is. So for that, first recall Cayley's theorem. So the Cayley's theorem actually guarantees that any finite group can be embedded inside a symmetric group. Basically that embedding uses the left regular action of the group on itself. So G is embedded inside Sn where n equal to the order of G. So this is what Cayley's theorem. So let us quickly go through the proof of Cayley's theorem. So basically for given any element sigma in G, we define this L sigma, which is a map from G to G, that actually takes given element x to sigma x. So the image of x under L sigma is just left multiplication of sigma on x. So that is why we are going to call this as left regular action. But anyway, from this it is clear that we can also talk about right regular action, but let us stick with only the left multiplication and left regular action. So it is an easy exercise to verify that L sigma is indeed bijective map. So now using this L sigmas, we can define this map L, which is a map from G to Sn. Since this L sigma is bijective, one can identify Sg, which are all bijective maps from G to G with Sn. So now given sigma, you just send it to L sigma, small l sigma. So that gives you an injective map from G to Sn. So that is what Cayley's theorem guarantees us. So this L is an injective group homomorphism. So even though the statement of Cayley's theorem actually sounds so simple, but it actually immediately guarantees that in order to classify all finite groups, it is enough to classify all subgroups of given symmetric group. But again, that is going to be equivalent problem and that is going to be very hard. But now using this regular action and the standard representation of Sn, we will be able to actually construct a regular representation of G. So let me just quickly tell you like how one actually gets the regular representation, but then after that I will explicitly define what it is. So from G to Sn, we have this left regular map. So that is an embedding. Then from Sn to GL and C, we have this natural standard representation of Sn. So where Sn acts on this GL and C by permuting the basis elements. But note that this Cn we can identify as a vector space with Cg, where Cg is the vector space of C spanned by this elements of G. So in particular G is the basis. So because of this identification, we can see that, so we have this natural composition map. So let's call this as phi standard, that the standard representation, and this natural composition map is going to give us the action of G on Cg. So that is what we are calling it as regular representation. So let us work it out how the action of G reflected on Cg. So, basically if you think about it, we have this basis G, G and G, and then we have to tell like, so what is going to be the composition map. So, from G, so let us call it L regular, from G to this GL of CG. So, this is the map we want to write down. So, basically given sigma, we define this L regular of sigma. So, which is going to be just a linear extension of this small map L sigma. So, note that L sigma is a map from G to G. So, now this can be extended linearly to CG to CG, because G is the basis and any set map from G to G can be extended to CG to CG linearly. So, very explicitly if you think about it, so here we take some linear combination of elements of G. So, then L sigma maps this element to summation A G sigma G, where G and G. So, this is how the explicit map is given. So, let us rewrite this map very explicitly. So, L regular, which is a map from G to GL of CG. So, which is given by sigma goes to L sigma. So, L sigma of summation A G G, G and G is given by summation A G sigma G, G and G. So, we have taken that left multiplication, extend that linearly to all elements of CG, that is what we have done here. So, if we rewrite this using the different index, so we can see that, so we can write this sigma G as X. So, then this G becomes sigma inverse X. So, then this is exactly equal to A sigma inverse X, X, X and G. So, this is what the image of L sigma. So, this is the image of L sigma, sorry, image of AGG under L sigma. Okay, so this already tells us that what happens to the action of basis under L sigma. So, maybe one can very explicitly write down as follows. If you just list all the elements of G as G1 etc. Gn, where if n is just the order of G. So, then what L sigma does? So, basically L sigma maps G1 to sigma G1, G2 to sigma G2 and so on, Gn to sigma Gn. So, in particularly you can see that if sigma is identity, then L sigma is just identity map on G, and if sigma is not identity, so then L sigma has no fixed point, L sigma has no fixed element. So, otherwise what happens, suppose if it has fixed element, then sigma G I should be equal to G I, that would imply immediately that sigma is identity. So, this actually immediately tells us that the matrix of L identity is nothing but the identity matrix, and the matrix of L sigma is going to be having 0 element on the diagonal, and then we do not know like, so it will have actually 0 or 1 as entries, but we do not need to worry about other entries. So, in particularly the trace of this LE is exactly n, and then the trace of this L sigma is exactly equal to 0. So, this immediately gives us the following observation. So, if we take this L regular, which is the regular representation of G. So, this is indeed left regular, but let us call it regular representation, not a problem. Then if we look at the character of this representation, then the character values is going to be exactly n if G is identity, 0 otherwise. So, we have very explicit description of the character. Okay. So, we define this map L regular. Anyway, I will leave it to you to check that this is indeed a group homomorphism. So, check L regular is a group homomorphism. So, since this is a group homomorphism, it defines a representation and we are computing the character explicitly for that representation. So, now once we have this information about the character, so we will be able to actually explicitly determine the decomposition of regular representation in terms of the irreducibles. So, if we think about it, recall that if we actually write down the regular representation as direct sum of irreducibles. So, then the multiplicity of given irreducible inside your regular representation is given by this inner product. So, which is chi regular comma chi I. So, this is exactly the multiplicity of V I inside this L regular or C G, let us write it as C G. So, by definition you can compute this inner product explicitly. So, we can see that this is exactly equal to 1 divided by the cardinality of G summation G in G chi regular of G bar chi I of G. So, this equality is by definition. So, now we know that this particular value is either the cardinality of G or 0 depending upon G being identity or not. So, that means this is going to be 0 for all G not equal to identity. So, only the following term will survive. This is 1 divided by cardinality of G, the cardinality of G times chi I of identity. So, that means this inner product which is the multiplicity of this chi I inside chi regular. So, that is exactly equal to chi I of E, which is the degree of this representation, which is d I. So, that means if you decompose chi regular as sum of irreducible characters, you can see that the coefficients are nothing but d1 chi 1 plus etcetera plus ds chi s. So, now by evaluating at identity, we can see that as a corollary chi regular of identity, which is exactly equal to the dimension of C G, which is the cardinality of G, which is exactly the sum of d I chi I of E, is exactly summation d I square. So, this proves an important identity that the cardinality of G is nothing but sum of this d I square. But we already know that the sum of this d I square is at most the cardinality of G, but from this corollary we immediately get that this is exactly equal to the cardinality of G. And as another corollary, we get that the following matrix coefficients, normalized matrix coefficients, they form an orthonormal basis of this CG. So, the set square root dk rho I j k, where k runs over 1 to s, and then given k we have this I j running from 1 to dk. So, there are d1 square plus etcetera ds square elements in this basis B. So, this is on orthonormal basis of this CG. So, we already know that this is indeed orthonormal subset of CG. So, now we need to prove that the span of this is entire CG, but since the cardinality of this B matches with the dimension of CG using the earlier corollary. So, we get immediately that, so this is indeed basis. So, this follows from the facts that B is orthonormal and the cardinality of B is exactly the cardinality of G, which is the dimension. So, we get this as immediate corollary. So, now we have this basis. Now, using this basis we will be able to prove that the irreducible characters they form an orthonormal basis for the space of class functions. But like I promised, let me first prove that the orthogonal complement of the span of these irreducible characters, that will be 0 inside the space of class functions. So, but that actually requires a little bit of preparations. So, we need, but the idea that actually we see in that proof, that is actually very crucial in representation theory. So, let me actually make some noise about how to do this for characters which comes from the representations. So, which is actually somewhat easy. So, what we want to claim. So, let me actually state the claim. So, we want to prove that this V, which is the span of chi I, where recall that these chi i's are nothing but the irreducible characters of this G, and this space is entire CG. So, this is what we want to prove. So, like I said, it is enough to prove that the orthogonal complement of this V inside this space of class function, that is 0. So, let us try to do that. So, like a baby case, maybe we can assume that chi comes from this orthogonal complement of V, but chi is indeed a character that comes from the representation, and chi is a character of a representation. I am just doing this special case just to demonstrate it is easy to prove for the characters that comes from representations. But note that the general elements in this space of class function, they are merely just class functions. They are identity on, so they take constant value on the conjugacy classes, that is the only condition we have. But here I am just doing the proof for the some element that is character of representation. So, now if it is a character of a representation and the representation space is actually non-zero, so then we know that this chi of E is going to be the dimension of the representation space. So, let me write it as degree of chi, and which supposed to be non-zero. Suppose the representation space is 0, then it is immediate that chi is 0, there is nothing to prove. Okay. So, since this is non-zero, now by computing this inner product between chi and chi regular, we can see that this actually this chi of v cannot be non-zero. So, let us compute the inner product between chi and chi regular. So, this is by definition you can see that this is summation chi g bar and then chi regular of g, g and g, I guess with the average. So, now you already know that chi regular of g what will be the values. So, that is actually non-zero only when g is identity. So, that means this is going to be exactly equal to 1 divided by the cardinality of g chi of E bar times the cardinality of g. So, which is exactly equal to chi of E. So, now you can see that chi regular can be written as linear combination of chi i's. So, now if chi is in the orthogonal complement of span of chi I, then this part is supposed to be 0. So, that means it forces that this chi of E is 0. So, that means the dimension of the representation is 0. So, that would force that chi is 0. So, we arrive contradiction by assuming that chi of E is non-zero. So, the proof is somewhat simpler whenever chi comes from the representation. But what happens if chi does not come from representation, it is just an element of this space of class function. So, let us take this chi which is just comes from this V perp, which is a subspace of this space of class function. So, then all we know that chi is indeed a constant function on this conjugacy classes. So, that means chi g is same as chi h g h inverse for all g h in g. So, this is the only condition chi actually satisfies. So, we actually take little bit detour. So, instead of proving chi is equal to 0, since it is a function on g taking complex values. So, it is enough to actually prove that chi of g is 0 for all g. So, in order to prove that, what we will do, we actually instead of proving chi of g equal to 0. So, we simply change the problem to like we construct an element in C g and then we try to prove that that element is 0. So, indeed what we prove summation chi of t in G is 0 instead of proving this chi is 0. So, if you think about it, both are equivalent only because these elements of capital G they form a basis in C G. So, it is actually equivalent, even though it looks like we are actually kind of going like using some complicated way of proving, but this actually indeed helps. So, again we have to use this regular representation, that is this left regular action of G on itself. So, that we will be able to prove. So, here is the ingenious way of doing this. So, instead of actually proving this element is 0, so what we do, we actually construct this following element and we prove that that element which is an element in the endomorphism of C G is 0. So, what we do, we construct this chi of t, L regular of t and t in G, and we prove that this is indeed 0. So, now how this implies actually immediately that the earlier term is 0. So, you can see that if we have this summation chi t L regular of t is 0, then we can make. So, let us call this an operator pi, we can apply on identity and then we again get 0 inside in CG. So, now this is an element in endomorphism of CG. But why this implies, if you compute this pi of E, you can see that this is exactly summation chi of t L regular of t applied on E t in G. But this is nothing but what? This is exactly equal to L t. So, L t applied on E is nothing but t, because we are just multiplying by t on the left. So, this sum is going to be exactly equal to summation chi of t t t in G. So, in order to prove that chi of t is 0 for all t, it is enough to prove that this pi is 0. Okay. So, chi is 0 if and only if pi is 0. So, why are we doing all these translations? So, because we know that this space CG, it is nothing but a direct sum of irreducible representations of G. So, we are going to use this complete reducibility, and then so we actually make use of that and then say that instead of proving pi is 0, we just restrict this pi to each irreducible complement and then prove that that is 0 for all I range from 1 to S. So, this is something we can do it because this CG is isomorphic to as a G representation V1 direct sum D1 direct sum etc., direct sum Vs direct sum ds. So, here these Vi's are all irreducible, inequivalent irreducible representations of G. So, this is the advantage of having this G action on CG. So, if you want to prove some operator is 0 on CG, then you just prove that it is actually 0 on this individual components that appear in the direct sum. So, we just prove that it is the restriction is 0, but if you think about it, we are just focusing on only one irreducible component. So, that means, so it is enough to prove that the following sum is indeed 0. So, let us call it pi I, which is exactly summation chi of t rho I of t, where t runs over in G. So, it is enough to prove that this is 0. So, it is enough to prove the following 0, because pi restricted to this V I is going to be exactly rho I, because the regular action when you restrict to V I, it is going to be rho I up to of course equivalence, but since equivalence are nothing but conjugation given by conjugation. So, if one map is 0, then another map is also 0. So, if you have a map S T S inverse, if this is 0, that will imply that T is 0. So, that is what we are using here. So, that means we can just simply prove that this operator pi I is 0. So, now let us look at this pi I. So, this pi I is nothing but summation chi t rho I t, and we want to prove that this is indeed 0. So, now we can actually drop this I. So, we can just simply call it rho, and then this is pi rho. So, where rho is, we can take it to be unitary irreducible representation of G. So, now the claim is this pi rho is indeed G invariant map. So, this pi rho lives inside home G V comma V. So, where V is the representation space. So, that is indeed a quick verification. So, let us do. So, if you take rho g pi rho g inverse. So, this is going to be exactly equal to summation chi t and then rho g pi rho of t rho g inverse, where t runs over g. So, now what we can do, because rho is nothing but group homomorphism, we can replace this by rho of g t g inverse. So, now if you replace like that, then what we get? We get exactly this left hand side equal to rho of g pi g rho of g inverse, which is equal to summation chi of g inverse sum s g and then rho of s, where s is running over g. Now, since this chi is indeed a class function, you can see that this is exactly equal to chi of s. So, then what you get is exactly equal to pi rho. So, that means this pi rho is nothing but G invariant map or intertwining operator. So, now if we go back to our analysis, since V is nothing but irreducible representation. So, since this V comma rho is irreducible, so that means this intertwining operator must be scalar times identity on V. So, by taking the trace, we can see that the trace of pi rho is exactly lambda times the dimension of V, which is the degree of rho. Now, since pi rho is given by summation chi of t rho t in g, we can see that this is exactly lambda times degree rho equal to summation chi t. So, chi t are complex numbers t in g and then the trace of rho t. So, this is what we get. So, if you think about it, so this is exactly equal to chi rho of t. So, which is since we have assumed that it is unitary representation. So, this is exactly equal to chi rho of t inverse bar. So, now you can see that. So, this entire term is exactly equal to. So, we can actually divide by cardinality of g and then multiply by cardinality of g. So, then this entire term is going to be equal to the inner product between chi and chi rho bar times the cardinality of g. So, that means lambda times the degree of rho is exactly equal to the cardinality of g times chi rho bar. But since chi we have chosen it from the complement, chi is coming from this complement of this span of chi I. So, from that you can conclude that this quantity is 0. So, that means lambda must be 0. So, that means pi rho, which is nothing but scalar times identity. So, that is supposed to be 0. So, from this we can conclude that pi that we started with, which is nothing but direct sum of. So, this pi is nothing but direct sum of d I pi rho I, and since each one of this pi rho I is 0. So, that would imply that pi is 0 and that would imply that chi is 0 as we promised. So, this is actually somewhat some indirect way of proving it, but you can see that if you want to actually get some information about some element action on CG. So, then we will be able to decompose that CG into direct sum of irreducibles, then we can try to understand how that endomorphism act on this individual direct sums. So, from there we will be able to get information about this entire map pi which acts on CG. So, it is really very important ingenious idea. So, this is actually kind of repeatedly used in representation theory. So, that is why I wanted to do this proof. Okay, I will stop here. We will continue with the second proof in the next class. Thank you.